Hello everyone, I am Ankit Kumar presenting our work on formally analyzing GossipSub, a P2P protocol used by applications such as Ethereum. We show that GossipSub and Ethereum are vulnerable to attacks by misbehaving peers. This work was done with my friend Max and our PhD advisors Pete and Christina at Northeastern University. GossipSub is a popular P2P protocol. It is used by applications like Ethereum and Filecoin, whose combined market cap exceeds $300 billion. It is a scalable and dynamic publish subscribe protocol. There are three important design considerations: fast delivery of messages, low bandwidth, and security against misbehaving nodes. How is fast dissemination and low overhead achieved? Full messages are transmitted on mesh connections, which are shown in solid blue lines. The degree of mesh connectivity is controlled to ensure fast delivery and low bandwidth. The hash of messages are gossiped outside of meshes, as shown using dotted lines. This leads to lower bandwidth overhead. If a peer is interested, it can then request full messages. The network is dynamic, with peers leaving and joining the network and meshes. GossipSub supports publish subscribe, where an application running on a node can publish messages to a topic without having to worry about who the receivers are. Nodes can subscribe to or unsubscribe from topics. A node can subscribe to and be a part of the mesh in several topics. Security against misbehaving peers is ensured by keeping track of metrics calculated by observing the behavior of peers locally. Some metrics are positive, meaning that larger values are better than smaller values. For example, time in mesh and the number of first message deliveries indicate positive behavior and are colored in green. Some metrics are negative, so larger values are worse than smaller values. Example as the number of invalid messages sent. Applications also contribute their own metrics. For example, P5. Some applications use this to make removal of publishers difficult owing to their high score. The first 5 metrics are topic dependent, while the rest are not. GossipSub detects peer behavior by combining the previously shown metrics in this scoring function. Notice that it's quite complex, with the green metrics being multiplied with positive weights and red metrics multiplied with the negative weights. These quantities are summed, multiplied with per topic weights, and the summation is then subjected to an overall cap. The score function protects against misbehaving peers locally. It calculates the score, which if less than 0 will get the peer pruned from a mesh. Peers having higher than average scores are also promoted or added to the meshes. We analyze this scoring function to figure out whether it really does protect against misbehaving peers. Analysis of the GossipSub protocol is not new. Previous work has focused on scenario-based testing or unit testing. However, for a protocol as complex as GossipSub, this analysis might not be enough. We are the first, to the best of our knowledge, to formally model the GossipSub protocol and reason about its scoring function using properties which might seem obvious but whose formal analysis revealed critical security problems. We started by modeling GossipSub in ACL2S, which is an industrial strength theorem prover in the first order logic. We used the prose specification as well as Golang code to write our executable model. We performed conformance tests to ensure that it matched the actual GossipSub protocol. In fact, our publicly available model has been identified as an official specification of GossipSub by its own developers. ACL2S allows us to perform large-scale simulations on GossipSub networks with real-world topologies involving thousands of nodes. The ACL2S model allows fine-grained control over network topology, application parameters, events, and messages for reasoning and simulation. We analyzed the scoring function responsible for security in GossipSub and found some vulnerabilities. The vulnerabilities were confirmed by GossipSub and Ethereum developers. We also registered it under a MITRE CVE. As an example, One of our simulations was performed on a real-life Ethereum testnet, shown on the right, based on previous work by Kai et al. The graph is visualized as a community graph where size of the nodes represents its degree, and similarly colored nodes are more closely connected than the others. On the left, we have the amount of time in seconds it takes to run our simulation on models of these real-life Ethereum testnets for various attacks. All of these simulations have been performed on 100,000 events. However, we can change the number of events that were used. Once we had a formal model in ACL2S, we came up with these fundamental properties. The fundamental properties state that peers who behave poorly will be demoted by their neighbors. Peers who behave better than average will be promoted by their neighbors. And promotion and demotion is entirely based on local peer behavior. Formally, promotion and demotion are defined by the score assigned to a peer, which is calculated based on its observed behavior. We decompose our informal properties into four formal properties as shown. Property 1 states that if after some point in time, the component of the score in a particular topic is continuously less than or equal to 0, then after some point in time, the overall score must also drop to less than or equal to 0. Property 2 states that if after some point in time, the negative metrics of a peer start increasing, then after some point in time, it is the case that the overall score for that peer drops and eventually it has to go below 0. Similarly, property 3 states that if after some point in time, the positive metrics of a peer start increasing, then after some time, it is the case that the overall score for that peer should increase and eventually it has to go above 0. Remember, the score is what informs us about a peer behavior. Finally, the final property states that identical metrics achieve identical scores. This is trivially proved due to referential transparency provided in ACL2S by virtue of it being a functional programming language. So we got counterexamples for the first two properties in Ethereum. However, in the case of Filecoin, we observed that all the properties passed. Here is a formalized version of property 1 in ACL2S. The property declares each of the universally quantified variables along with their types. PTC is a map of pairs of peer and topic to topic-based counter values. These topic-based counter values are used to calculate the metrics we talked about in the previous slides. P is a peer and top is a topic. So the property says that if the pair of P and top appear as a key in PTC, which is a map, they have corresponding topic counter values, and if the topic score for the topic is non-positive, then the overall score for peer P is non-positive. On the right, we see counterexamples, values for the property shown, which suggests that there are topic counter values for which a non-positive topic score does not imply a non-positive overall score. Notice that the property we have here is a non-temporal version of property 1. When we simulate an Ethereum GossipSub network to reach these counter values, we notice that the state of the network starts looping back to this state, disproving the temporal version of this property as well. The reason that property 1 holds for Filecoin is that the maximum positive score is dominated by the minimum penalties due to misbehaviors. So any misbehavior is enough to bring the overall score below 0. There is a cap applied to the sum of the topic-based components of the score. So if there is a decrease in the topic-based scores such that the total is still higher than the cap, then this drop is not reflected in the overall score. In case of Ethereum, this is what happens, and hence property 2 does not hold in the case of Ethereum. However, Filecoin disables this cap and hence it satisfies property 2. Based on the insights we got from the counterexamples to the two properties in the case of Ethereum, we developed attack gadgets. On the slide, you can see the shape of a gadget. More details and analysis appear in the paper. but these attack gadgets make it easy to understand and construct the attacks. As an example, an AG1 attack gadget is shown in this slide, where peer A is attacking peer V in a single topic. That is, messages in the green topic are being dropped. However, V is unable to detect this misbehavior from A and is also unable to prune A from its own mesh. Attack gadgets can be combined to form various attacks, including eclipse and network partition attacks. We constructed, simulated, and verified these attacks using our ACL2S model in the context of Ethereum. To conclude, we present an official, open, formal, fully executable, and cross-validated model of GossipSub, which we use to find attacks where misbehaving peers appear to be honest. And these attacks can be scaled to create network-wide disruption. Thank you.